asking, we need to move on to the next speaker.
Okay.
So the next talk is given by Michael Zervas, the Chief Executive Officer and co-founder of Ligentec. And his talk is entitled Hybrid 3.5 Silicon Nitride Integration, the Dielectric Platform Perspective.
I took it on a PDF. That's good. Thank you. Okay. Good morning, everybody. My name is Michael Zervas, and I will speak about hybrid and heterogeneous integration and present the challenges and opportunities and the views from a dielectric foundry perspective. I'm a co-founder of Ligentec. Ligentec is a dielectric foundry located in Lausanne, Switzerland. You can see our location is opposite of the EPFL facilities, and we have a very nice view to the Lac Le Mans. Ligentec specializes in high confinement of thick silicon nitride, which gives certain benefits. And the main motivation for high confinement, the high thickness silicon nitride, is that as you increase your nitride thickness, you have the benefit of dropping your chip cost because your chip becomes smaller and reducing dramatically your propagation losses. So at the high confinement end, we can see bending radius on the nitride platform down to 10 microns without any loss on the curves. And we can see a typical loss of 0.1 dB per centimeter and local losses in R&D processes down to 0.7 dB per meter, which is really, really, really low. Now, silicon nitride is actually a flavor of silicon photonics. And silicon is not a dielectric, it is a semiconductor, but it can be seen as a middle ground between 3.5 material full dielectric with dark band gap and full dielectric material like silicon nitride. And if we compare these two materials, we will see that silicon nitride has some benefits, starting the larger transparency window. So silicon nitride is transparent down to the UV. 0.3 microns is a very comfortable range for silicon nitride, while in the case of silicon, you can go down to 1.1 micron. And this really comes down to the physics. The band gap of a semiconductor material is on a few EVs, while the band gap of a dielectric material is several EVs, 5 EVs or even more. Second limitation is the power that these materials they can handle. In silicon photonics, your power levels is a few tens of milliwatts, while in the dielectric platforms, you can really put watts. We have tested in our chips up to 7 watts CW power. And again, the physical mechanism behind is that there is no two-photon absorption and a large band gap to work with. The losses of the material and some of the benefits which make it easy to scale up is that you have a lower index contrast compared to your cladding and compared to silicon. So it reduces your distributed backscattering by a factor of 10. It decreases the optical path length error by another factor of 10. And at the same time, the material is less thermal sensitive. So if you need to have some thermal designs, it drops the power consumption that you need by a factor of 10. Of course, if you want to tune such a material, you need to put 10 times more power, which is a trade-off you need to make in the design phase. But it also provides a unique opportunity for innovation, and that is to actually stack many layers of active functionality of waveguides, one on top of another, and make a full 3D circuit. In silicon nitride, the material is amorphous, so you can literally and readily deposit one layer on top of the other and have different functionality on each layer. In SOI platform, that is not possible because the crystalline silicon, you need to bond it, you need to transfer it from another crystalline wafer source. But silicon is more mature. It has modulators available, taking advantage of the different plasma phenomena that can go to gigahertz speeds, and they have a rather compact footprint. There is a ready photodetector integration that is done with typical silicon germanium, which again is very efficient, it goes very fast, and it is ready today. Silicon nitride has some answers to these problems, but still in the research phase. Where both of them are having a limitation is that there is no efficient light source integratable into these platforms today. And this is where a lot of hybrid information and hybrid technology comes into place. I talked before about hybrid, and in this talk I will use the word hybrid and heterogeneous integration to mean the same thing. And I take as a definition for heterogeneous integration what is stated at ITRS. This is an electronics technology roadmap, but their definition is very clear. So heterogeneous integration refers to an aggregation of pre-manufactured chips into a system that increases the functionality of such said system. This means that you have chips, you put them together in a type of system-in-package approach. So what are the technologies and possibilities to combine 3-5 materials or other materials into a dielectric platform? And this is a very high-level overview. So all in all, we can group it to 6 main technologies, with the first 4 having some form of bonding and the last 2 being closer to a microassembly. So the first option is to start with molecular bonding. Molecular bonding means that you bring in intimate contact your 3-5 material and your dielectric material, and van der Waals forces become dominant so they can stabilize the said material on the dielectric wafer. But to do that, you need to take your 3-5 wafer, dice it to small pieces, reconstitute another wafer, and then bring them into the contact and bond them, remove this material. The light on this comes evanescently from one layer to another, and since it's a wafer level process, makes it pretty scalable. But because there is also this added complexity of putting these things together, the cost goes high. And you don't have the possibility to actually test each wafer, so to combine known good dyes, it increases your cost and potentially drops your yield. Now, the assembly effort for this is low because we know how to bond wafers. For the last decades, we're pretty good at that. And the active design that you need to design something specially for this technology, but it is also something that is known. But putting all this together and making sure that it yields and you have a good chip at the end is difficult. Because every small particles, every small defect you have in one surface or the other is going to destroy both chips, not only one. To reduce this risk, there is the glue bonding. The glue bonding is the same approach as before. So you take your reconstituted indium phosphide wafer and your dielectric wafer, but in between them now you put some glue material like SU8. This glue material can take and reduce the sensitivity you have to defects and allows you to increase your processing window. The light again goes evanescently from one chip to another. The process is again scalable because it's a wafer level process, but you have these extra operations which increase your cost as before. But since your indium phosphide devices are not fully assembled, they are not fully done, you are not limited to a tight alignment confinement that you have in spot converters, as we will see at later cases. And again, a similar design can be used. And your main benefit is that you gain on reduced manufacturing effort, higher yield. Transfer printing. I know there is someone from Accelerate in the room and will speak about transfer printing after me. What I would like just to comment is that it's a very innovative technology. It is really scalable and really smart. And what you do is you only take the epi layer from the full wafer and transfer only this epi layer to the dielectric cell that you want. The challenges that are posed on this, in my opinion, is that you need a very special epi layer. You need a special design for your active components to be compatible with this approach. And when you start doing this transfer printing with the soft stamps, it's also a technology that it is not very well understood and known to make sure you have all the yield. So you need to learn a lot in the manufacturing line to drop this central barrier. Now, the most promising, at least on paper, approach will be the heteroepidaxy. It's like the holy grail of combining different materials together as long as you can epitaxially grow. They go a little bit outside of the definition I gave before for hybrid integration, but it's still relevant. And the idea here is that you have certain areas on your wafer that you can grow the 3-5 material selectively. And you can do this one at large wafer sizes, 8-inch, 12-inch, so very scalable. The cost can be seen to be very low. It's a wafer process. There is no reconstituted wafer, so lower operations. There's no assembly because everything is lithographically defined. But the actives needs to be spatial designed and very spatial designed, and to actually grow optical grade material on silicon is really non-trivial. This makes it a very, very difficult to build and to have actually working devices. Then on the microassembly side, we can see the bud coupling, which is the most straightforward approach that people can think. And it is really putting two chips edge to edge with appropriate spot size converters and aligning them. This is less scalable because it's a microassembly. The cost of it, though, can be seen as low for low volumes because you just take two chips and put them together. But the assembly effort is higher because the spot size that you have to work with are pretty small. And as a rule of the thumb, your alignment tolerances and how accurate you need to be is 1/10 of your spot size. So you take a spot size that is 3 microns and assume it Gaussian, then you need to be within these 300 nanometers, which is challenging. You can use larger mode size, and this, of course, definitely going to help. But then as you increase your mode size, it means you need more material on the 3.5, which gives other challenges or problems to the process. Now, the active design effort for bad coupling is almost zero. You can take almost ready components and put them together. And I emphasize the almost, because there's always some modification that is needed. And the manufacturing effort from the dielectric side is, again, low, because you get more or less what you already have and put it close together. The last approach is flip chip solder. And here you use the solder bumps or solder stripes, and this electrical layer helps you with the alignment of the 3.5 chip, because the surface tension of the solder will auto-align your chip to whatever lithographic layers you have aligned your metal layer. And you can make it either edge or vertical. For example, if you go with a vessel on top, and you have the benefit that at the same time you make also your electrical connection as well as your optical connection. But you need the next operation, and that is to put the whole solder layer down, which is a standard process, but you need to take into account the wettability of it. You need to take into account the under bump metallization and actually the bump themselves manufacturing. And usually these are not on the same level, so the moment you start working with non-planar topographies in nanoengineering becomes challenging. The assembly effort is reduced because of this self-alignment and the active design. You need to make sure that ideally all your electrical contacts are on the bottom where you do the solder bump, and that you have enough space between your electrical contacts and your optical mode to not have any problems there. From the manufacturing side, on the dielectric side, you need to put this RDA layer down. Now, how we at Ligentec approach hybrid integration. And Ligentec technology comes into 2 flavors, the AN150 for the visible and the AN800, which covers from 1280 to 1650 nanometers. And another one key characteristic of our technology is that the technology is modular. This means you can have an a la carte type of process while the process is still standard. And it is not modified or customized per base, gaining the benefit of stability. And at Ligentec, we have developed 2 modules that address the hybrid integration. The first module will be the X2 module, which allows you to put 2 layers of nitride, one on top of the other. And with this, you can adjust your independently the top layer to whatever application requirements you have, and the bottom layer to maybe a completely separate application requirement. And these 2 layers, they communicate with an optical via, so they are not meant to guide light in between. And the second module that is relevant for hybrid integration is what we call local cladding opening for bonding and sensing. And here we remove the top oxide from the nitride, making a thin layer of about 100 nanometers that you can evanescently couple and bond the 3.5 material either with molecular or glue bonding to the silicon wafer. Now, some example. Under the DARPA program course and with UCSB, we built a chip assembly, which looks like the image on the left. And the Ligentec chip is this guy here. This is a silicon nitride interposer. And this silicon nitride interposer has 2 nitride layers. And the reason in this case we use 2 nitride layers is because the bottom layer here, it is meant to do Kerr frequency comps. And the top layer, it is meant to make linear functionalities covering from 1050 all the way to 250 nanometers, so 1,000 nanometer operating wavelength. And to this chip, it takes the light from the laser here, and you can see a close-up here, where it is band coupled, and you have mode matching between the silicon chip, external cavity laser silicon chip, and the silicon nitride interposer. And you can see already some parts of the passive. And on the other edge of this chip, it goes to certain optical fibers, and it goes to in-gas photodetectors that are integrated into this package in the microassembly, and also communicates with the glass chip. This is a PLC that does also another nonlinear optical functionality. What is not shown in this picture, but I can tell you it is placed on top of it, is also a gallium arsenide polarization rotation for second harmonic generation. So the dielectric platform has a lot of flexibility of connecting all these different optical components, matching the mode to what you need, operating on a broad wavelength, and doing all the connections with very low losses and very high efficiency. And as I said before, this chip works from 1050 to 250, and you can see this is an image just of a dichroic filter where it splits in one case the 1050 and the 2050 in the other case. And this is done on a single chip, so it has a really, really broad operating wavelength. Now, as we're a foundry, I just wanted to put this slide in. Maybe it's too complicated, but I think it's interesting to appreciate how much work actually is on the substrate removal and in the bonding, because when we say bonding, we only think one operation. But usually on all hybrid integration, bonding comes with a lot strings attached and a lot of other work that needs to be done. So we'll take the example of a photonic damascene process where we do our patterning, and then we deposit our material, and then we CMP this said material, and then we clad it on the top. But now the first thing that we need to notice is that cladding needs to be bonding quality. Bonding quality means that your roughness is ideally better than 1 nanometer. So we need to polish it at some stage. For example, in this integration flow from 2016, we just bond here. But then you need to thin down this layer, and accurate stops just 100 nanometers away from the silicon nitride. And I can tell you that this is difficult to control it across the whole wafer with certain tolerances, so all the devices will work. So we need to be very careful. And then another aspect that we need to take into account is that if we speak about molecular bonding, then you need to introduce some gas release channels. So you need to have somewhere another layer of lithography. So in this process, you can see it here, that it opens some structures left and right of the waveguide that it can take away any gases that are generated during this process. And like that, we are ready to bond. So in another part, we take a lithium niobate wafer, and this lithium niobate wafer, it is properly made to have a thin film of lithium niobate, some oxide, and maybe a silicon handle, and you dice it in an appropriate condition, and then you bond it by thermocompression bonding to this location here, and you can see the channels help take away all the gases generated in the process. But now you have this whole wafer on top and no patterning on the active material. So you need to take away the substrate, so you go to substrate removal, but the substrate is thick, so it is not a trivial process. And you start thinning it down in step 1, in step 2, and then when you thin it down sufficiently, you still have the buried oxide layer or some sacrificial layer of that material, which you need to remove again here. And the moment you reach to this point, you say, okay, I'm done. But then you didn't do any processing on the 3,5 material, or in this case, the lithium niobate material. You didn't put the electrodes to connect it, so it's not electrically active. And you didn't passivate it to protect it. So this processing comes after this step. So these operations, where everything can go wrong, it's just what you will call bonding. And it doesn't show the reconstitution of the wafer. Now, challenges of this one is, as you can see in this image, these green waves are actually particles. So we had the contamination on this specific chip. This means that if you try to put a material here, these particles are going to break your material, and you are going to have a loss. It will not work, so both chips are going to be lost. And this is an AFM image that I just want to show that you need to be really flat and really uniform. So you can probably get a bonding with a 2 nanometer RMS, but ideally you want to be lower than that. Now, if you put all this together, you can make some really interesting devices. So this is a silicon nitride chip with a lithium niobate bonded. And you can see that the light comes from one side of the chip to another. And with a lithium niobate on silicon, you can make 100G modulators. And you can put as many of these modulators as you like. And again, this is the work done with the DARPA program cores. Again, working on bonding, you can say, okay, lithium niobate is one wafer, but what about if we want to put gallium arsenide? And in this paper from Stanton, again under the DARPA course program, we do just that. So we do the silicon nitride waveguide, and then we bond on top of it a gallium arsenide device. And this gallium arsenide device does a polarization rotation, that's why it's a bit offset, and the second harmonic generation. But now we see another trick in the book is that the gallium arsenide has a different refractive index as silicon nitride. So this means to take light out of the gallium arsenide or 3,5 materials is not that trivial. You need to taper it down to very small sizes, or you need to find some ways around it with clever engineering how to take the light out of the gallium arsenide and back to the silicon nitride if you want to do this. The other way around is a bit more simple. And you can see here that you go from a dominant TM mode to a dominant TE mode. And again, the wavelength that this thing operates is unique. So you can do that around the 1 micron, the second harmonic generation from, if I remember well, a 50-50 pump. Now, we can do glue bonding. And in the case of glue bonding, you can see that there is the addition of the glue layer here. This is an SU8 layer by you. Again, this work is done under the DARPA course program. And there is this bonding window, and then you bond your indium gallium arsenide, indium phosphide chip to it. And you do all this post-processing to put all the electrical contacts we said before. And if everything goes well, you get a photodiode. that can work for the balance case with 0.68 responsivity and work up to 8 gigahertz. There's a second generation device, and I think our collaborators, they will give a talk about it at OFC. They go further in frequency and improve also the slope here. What is also not shown here is that you can combine molecular bonding and glue bonding. So you can combine, say this part will be molecular bonding and gallium arsenide, and that this part will be a glue bonding with indium phosphide. And then you can make even more complicated and elaborate chips that increase further than functionality. And this is the benefit of the flexibility of the dielectric platform. The last I will talk is on Shetterrapidax Integration, and this is work done under the Moicana program. This is a European funded program that we do participate with 3.5 labs and VLC Photonics. And in this case, we deposit the 3.5 material inside a special opening. And the main trick, assuming you get this one right, is also how do you take the light from the 3.5 material to your silicon nitride waveguides. And one of the approaches is to use a special type of waveguide that may look like this and may take the light from the indium phosphide and couple it to the silicon nitride waveguides. My last slide, just to say, we have, Ligentec has a high mode confinement technology with low loss, high power operation possibility, small footprint, and it comes with a PDK giving full creativity to the designers, but it's also a very flexible platform that you can do hybrid integration. It is tested and has modules developed specifically for that, that can increase the possibilities for laser modulators and detectors to be integrated into a single package solution. Thank you very much.
Thank you, Michael. Any question from the audience? Well, I have one myself. You talk about hybridization platform. So, who is the main user of this hybridization platform? I mean, it's more something for academic use, or is already used by more industrials.
So, hybrid integration is how all the silicon photonics is done, because there is no laser possibility in silicon, so you need to do this type of hybrid integration. Outside of the telecom and datacom market, there is a lot of exploratory work that is investigated, and there are a lot of interest in markets such as sensing markets, markets such as augmented reality and LiDAR, and to some extent, but not very high, in quantum technologies. I'll expect more, but it turns out that that is not the case.
Okay, Michael, so thanks again for the talk.